This video is going to be about the Arrhenius equation. But before we get on to the Arrhenius equation, I just want to revisit the rate equation. So we know that rate is equal to the rate constant times by the concentration of the reactants raised to the power of their order. So I've just got a generic rate equation here. So we're saying that the rate is equal to the rate constant times by the concentration of A to the power of 1, because it's obviously a first order reactant, times by the concentration of B to the power of 2, because it is a second order reactant. Now, if we increase the concentrations of our reactants, then we're going to increase the number of reactant particles in a fixed volume, we're going to increase the frequency of collisions, we're going to increase the rate of reaction, and that makes sense. But we also know that other than increasing the frequency of collisions, there are other ways of increasing rate of reaction. For example, increasing temperature. Would increasing temperature increase the concentration of either of these two reactants? No, it wouldn't. Another thing we can do is perhaps add a catalyst and alter the activation energy. Lower the activation energy would increase rate of reaction. Would that affect the concentrations of our reactants? No. So we already know the effect of temperature and of the activation energy on the rate of reaction, and those factors are encapsulated here in the rate constant. So up until now, we've talked about the rate constant in terms of how to calculate it and how to obtain its units, but we haven't actually specified what it is or what factors affect the value for K. So K can be derived from the Arrhenius equation. Okay. So the Arrhenius equation is K is equal to A exponential negative activation energy over the gas constant times temperature. So we have our rate constant with no fixed units. A is called the pre-exponential factor. And it is a number that represents basically the likelihood of collisions. We have e to the power, okay, this is an exponential. It is the inverse of the natural logarithm. We have EA, which is activation energy. Which is measured in joules per mole. We have R, which is the gas constant, which is 8.31 joules per Kelvin per mole. And we have temperature, which again is going to be in Kelvin. So these are all of the important parts of the Arrhenius equation. Now, activation energy, obviously the energy required for successful collisions, the gas constant and the temperature obviously determine the energy that those particles have, the pre-exponential factor, the likelihood of those collisions occurring. So in terms of the effect of changing activation energy and changing temperature on the rate constant, remember this is e to the power of negative EA over RT. So it's to the power of a negative number. And if you have something raised to the power of a large negative number, then the number itself is smaller. Whereas if you've got it raised to the power of a smaller negative number, then the number itself will be slightly larger. All obviously small numbers, but compared to each other. So if this value for EA over RT, if that value increases, then the value of K will decrease. And if this value, the overall value for EA over RT decreases, then the rate constant will increase. So for an example, if we increased temperature, for example, so if I increased temperature, it would make this whole expression smaller, which would mean the rate constant would be higher, which makes sense. Increasing temperature increases rate. If I decreased the activation energy, again, I would make this whole expression smaller, which would make the rate constant larger, which would increase the rate of reaction, which again would make sense. So they could potentially give you the required information. Perhaps you've already calculated activation energy, they've already told you the temperature, the gas constant is a fixed value. You might know the rate constant and you'll have to rearrange for the pre-exponential factor. There are going to be questions where you have all of the values you need and you need to calculate one of the unknowns. Potentially you'd be given all of the values bar 1 and you'd have to calculate that, and we'll talk about how we do that later, and then substitute back into this formula to calculate the unknown. But in this format, if you know the values, then this is the format to use. However, if you don't know all of the values, the best way to find them out, or certainly the pre-exponential factor and the activation energy, is to plot a graph, which are known as Arrhenius plots. So Arrhenius plots rely on this equation being expanded so that it fits the equation of a line. And the first thing we need to do is to get rid of this exponential. Now, for those of you that are taking A-level maths, if you haven't already, you will certainly cover exponentials and logarithms and cover them in a great more detail than we are going to require. Okay, so logarithms for chemists. Take your calculator. This button here, ln, that is natural log. Okay, so if you want to take the natural log of something, you press that button and it opens up a bracket and you can put the number in and it will take the natural log. If you want to do the inverse of that, you press shift ln and that brings up e to the power. And that's all you need to know. As long as you know that the natural log is that button there, ln, and that the inverse of that is shift ln, e to the power, exponential, then you will be able to carry out all of these calculations. So, the first thing we need to do, I want to get rid of that exponential. So just like when we manipulate any equations or any formulas, we do the opposite. Well, the opposite of e to the power is ln. It's the natural log. So we're going to take the natural log of everything in this equation. So we start off with k is equal to a e to the power of EA over RT. We are going to take the natural log of everything in that equation, which is going to leave us with ln k, natural log of k, is equal to ln a. That exponential is now gone, so it's just going to be minus EA over RT. Now there's one more thing we need to do before this can be used, and that is we're just going to expand this fraction slightly. So we're going to change it to, so we're going to keep ln k, that doesn't change, ln a. I'm going to keep minus EA over R, but we want to just get rid of this temperature. Well, we don't want to get rid of it, we just want to expand it. So we make it times 1 over temperature. And now this version of the Arrhenius equation is more useful, because what you can do is equate this to the equation of a line. So the equation of a line is y equals mx plus c, while ln k is our y, ln a is our c, our EA over R is our m, our gradient, and this is our x. So being able to expand the equation like this means that if we plot 1 over temperature as our x-axis against the natural log of k on our y-axis, where it intercepts the y-axis will be the ln a value, which means if you took the e to the power of that value, you would know a, the pre-exponential factor. If you took the gradient of the line, it would be equal to minus EA over R, which means that if you multiplied it by the gas constant, you would have minus EA, which you could then just make into a positive value to get the value for the activation energy. So this expanded form of the Arrhenius equation is really, really useful, and it allows us to calculate the value for the pre-exponential factor and also the activation energy. So the plot itself will look a lot like this. So on your x-axis, you're going to have 1 over temperature. On your y-axis, you're going to have the natural log of k, and you'll end up with a linear relationship because it's a logarithmic graph. So you're going to get a linear relationship. Now, what you can, first thing you do, where it intercepts on the y-axis, that is c, that is equal to the natural log of a. So whatever value that is, let's say for example it was -2, just picking a number there. Okay, so if it was -2, so ln a is equal to -2, but I don't want to know ln a, I want to know a. So we do the inverse of ln, which is shift ln, which is e to the power of -2, meaning the value for a in this hypothetical example would be 0.135. Now, if we wanted to know the activation energy, we would work out the gradient of our line. So the gradient is equal to dy over dx, which is equal to minus EA over R. So once we know our gradient, if we took our gradient and multiplied it by R, it would be equal to minus EA, and then you can just flip the sign to get the value for activation energy. So by taking an Arrhenius plot, you can work out the pre-exponential factor and you can work out the activation energy. Now, in order to get the data you would require, in order to make an Arrhenius plot, what you would need is repeated data for the same experiment where you have the rate constant at different temperatures. So keeping all the concentrations of all of your reactants the same, all that's going to change is you vary the temperature of the reaction, and you can calculate the rate constant at each of those temperatures. And if you've got repeated data showing different rate constants at different temperatures, you could then plot this graph of 1 over temperature in Kelvin, okay, because it's 1 over, it's Kelvin to the -1, okay, against the natural log of the rate constant, and then from that you can work out the pre-exponential factor and you can work out the activation energy. Now, this is the kind of question that is going to come up. So we've got an experiment here that's been repeated at different temperatures, and the rate constant has been calculated at those different temperatures. Now, the temperature itself and the rate constant itself you cannot use directly. Remember, the Arrhenius plot is going to be 1 over temperature plotted against natural log of k. So we need to calculate those values first. So to get the natural log of anything, it's nice and simple. You just press the ln button on your calculator and then you type in the value. So ln 6.13 times 10 to the minus 5 is minus 9.70. Natural log of 2.75 times 10 to the minus 4 minus 8.20. Natural log of 8.25 times 10 to the minus 4 minus 7.10. And then finally, natural log of 8.23 times 10 to the minus 3 minus 4.80. So there would usually be a mark for this as long as the entire column is correct. So you can't afford for any one of those to be wrong. You need to get all of them right for that mark. The next column here is 1 over temperature. Now we're given the temperature, it's already in Kelvin. Perhaps they might give you the temperature in centigrade and you'd have to convert it to Kelvin first before you took 1 over. It has to be in Kelvin. So 1 over 700, 1.43 times 10 to the minus 3, 1 over 727, 1.38 times 10 to the minus 3, 1 over 746, 1.34 times 10 to the minus 3, and finally 1 over 793, 1.26 times 10 to the minus 3. And again, there'd be a mark for that as long as you got the whole column correct. So we need to plot that, and you'll notice they haven't given us a scale, so we're going to have to work out our scale. Now it does not need to go through 0, 0, but we are going to talk about the limitations of that later on. If you want to calculate A, the pre-exponential factor, then it makes life a lot easier if your plot goes through 0, 0. We don't need to know A, we're not trying to work out A, so it actually makes more sense to only use the values, sort of a range of values that are going to be useful to us so we can get a good line and a good gradient. Okay, so because we're not interested in calculating A, we don't need to start at 0, 0. So we're going to have 1 over T, 1 over temperature, as our x-axis, which is going to be Kelvin to the minus 1. And I'm going to start at 1.20. Now, when you're plotting an axis that's got standard form, just put the standard form in the label. Make life a bit simpler. These are all times 10 to the minus 3. So we'll just put times 10 to the minus 3 up there. And now we can just plot whole numbers. We don't have to worry about the standard form. So I'm going to start at 1.20 and I'm going to go up in 0.05s. So 1.25, 1.30, 1.35, 1.40, 1.45, and that fits nicely. On the y-axis, we're going to have the natural log of k, which doesn't have any units. Anything that's taken to a logarithmic value doesn't have any units, so you don't need to worry about that. So we need to go from minus 4.8 to minus 9.7. So I'm going to start at minus 4 and just go up and go down in ones. That fits quite nicely. So now we just got to plot it. So at minus 4.8, it's 1.26. So at 4.8, it's 1.26. At minus 7.1, it's 1.34. At minus 8.2, it's 1.38. And at minus 9.7, it's 1.43. and then we have a nice linear relationship. Again, because this is a logarithmic graph, you're going to get a linear relationship. So we can draw our line of best fit through there. Now, what is required is that you remember that the gradient is equal to minus EA over R. So if we write it out again, I mean, they've given us this expression here, which has got everything in it apart from they haven't expanded that fraction. So if we rewrite it, so ln k is equal to minus EA over R times 1 over T plus ln A. So this is Y, this is X, this is M, this is C. Okay, so Y equals mx plus C. So we know that our gradient is going to be equal to minus EA over R. So we need to calculate our gradient. So our gradient is equal to dy over dx. So let's look at the y-axis first. So it's gone from 4.8 to 9.7. So negative 4.9. And the x-axis has gone from 1.26 times 10 to the minus 3 to 1.43. So that is an increase of 1.7 times 10 to the minus 4. So negative 4.9 over 1.7 times 10 to the minus 4 is minus 28823.5. Now that value there is equal to minus EA over R. Okay, so to get EA, we need to multiply it by R. So minus 28823.5 times R is going to be equal to minus EA. Now R is 8.31, which we are told up here anyway, if you hadn't remembered that. So minus 28823.5 times 8.31 equals minus 239523, and that is in, remember, joules per mole. So we want that, that's the negative EA, so we want positive EA, so therefore EA is equal to positive 239523 joules per mole. But again, we want it in kilojoules, so we need to divide by 1,000, giving us 239.5 kilojoules per mole, and there is our answer. Okay, so remembering that the gradient of the line is equal to negative EA over R. So as long as you work out the gradient and multiply it by R, R being the gas constant, then you will get the negative activation energy, which you just make it positive if you want to know the positive value for activation energy. And always look out, remember, activation energy is measured in joules per mole, and that is because of the units of the gas constant. Because the gas constant is measured in joules per Kelvin per mole, the activation energy is therefore measured in joules per mole. So look out for what they want the units for your answer to be in. If they want kilojoules, you're going to have to convert it at the end. So the other thing they could ask you to calculate using an Arrhenius plot is the pre-exponential factor. Now, in order to determine it directly from the graph, you would need a y-intercept when x is equal to 0. So straight away on this graph, it's not going to be possible to directly determine it, because number one, we don't have a y-intercept, and even if we did, our x-axis does not go to 0. So we are unable to get the pre-exponential factor from this graph. If we did have a y-intercept when x was 0, wherever it intercepted the y-axis, that would be equal to the natural log of a. So if you just took the inverse of that, you took e to the power of that value, you would get the value for a. But there is nothing stopping us from calculating a using the Arrhenius equation, because now we have all of the information that is required to calculate a, because we have all of the values apart from a. So if we just remind ourselves that the Arrhenius equation in its normal format is k is equal to a e to the power of negative ea over rt, we have all of those values. We know k, because if we just pick any one of these experiments, I'm going to choose experiment 1. So I've got the value for k, I've got the temperature, I've calculated the activation energy already, and the gas constant is constant. So we know everything apart from a. So all we have to do is rearrange for a. So a is going to be equal to k over e to the power of negative ea over rt, and then just substitute in the values that we have. And again, I said I was going to use experiment 1, so that's going to be 6.13 times 10 to the minus 5, that's the rate constant for experiment 1, over e to the power of negative activation energy. Now remember that in the Arrhenius equation, the units for the activation energy are joules per mole, because the gas constant, is in joules per Kelvin per mole. So the activation energy will be in joules per mole. So I can't use this value here, 239.5, because that's kilojoules per mole. I need joules per mole, so I need to use this one here. So it's going to be 239,523 over the gas constant, which is 8.31, which is always given to you in case you can't remember it, times by the temperature. And again, I chose experiment 1, temperature was 700, which if I type into my calculator, so 6.13 times 10 to the minus 5 over, and then to get the exponential, it's just shift natural log to get the inverse, so e to the power of negative 239,523 over 8.31 times by 700, 700 not 70, and close the brackets, giving us 4.67 times 10 to the 13, and that is our value for a. And what we can actually do is, if we take the natural log of that value, so just ln answer, this is when our y-intercept would occur. So this line wouldn't intercept our y-axis until 31.4. So if we were plotting a graph and looking for the y-intercept, we would find it at 31.47. That would be ln a, and we could then take the inverse of that to get our value for a. And the final thing I just wanted to talk about was the units, just making sure we're very, very clear on the units. So the rate constant has no fixed units. It depends entirely on the order of the reactants in the rate equation. So we've done that, where we've been working out what are the units for the rate constant. The activation energy is always in joules per mole, because the gas constant is in joules per Kelvin per mole, and the temperature is in Kelvin. But what you should notice, if you look at just this fraction, okay, I've got joules divided by joules, so they cancel. I've got Kelvin to the minus 1 times Kelvin, so they cancel. I've got moles to the minus 1 divided by moles to the minus 1, so they cancel. So actually, this entire expression here, this minus EA over RT, all of those units cancel, which leaves you with, I mean, the exponential doesn't have any units, it's just a mathematical function. So that leaves us with rate constant is equal to A. So the units, whatever the units are for the rate constant, the pre-exponential factor will have the same units. So if the rate constant was just seconds to the minus 1, for example, then the units for A would be seconds to the minus 1. If the rate constant was mole to the minus 1, decimeter cubed, second to the minus 1, then A would have the same units. Okay, so K, the rate constant, and A, the pre-exponential factor, always have the same units because all of the units for activation energy, gas constant, and temperature, they all cancel out.